It's great to be here. This is a joint work with Umut from North Carolina State University and Aram Grigoryan from University of California, San Diego. This is about assigning students to schools. And what do I mean by that? It's still a very simple question. Here is an overview. We are going to have students. I'm going to denote them by S. We are going to have schools. I'm going to denote them by C. We are going to try to find an assignment. Mu S is the assignment of student S. It turns out to be school C. Students are going to have preferences. Schools are going to have priorities. And we are going to look at the stable assignments. And we all know what stable assignment is. A matching assignment is stable if when student S prefers some school C to his or her assignment, mu S, then the C should be filled with students with higher or equal priority. Right? This is what we are going to study. But on top of this question, we are going to introduce a match quality. This Q is the quality of match between student S and school C. What can this be? This could be pretty much anything you can imagine. It could be the distance between the student's home and the school. It could be whether the school is a good fit for that kid's abilities or not, to the extent you can match that ability. And what we want to do is actually we would like to pick a stable matching. And we want this stable matching to maximize the sum of those match qualities. This is student S. This is his or her matching. This is the quality that we are generating by assigning S to this school. And this is the sum over all students. And we are going to maximize this amount over all stable matchings. That's what we are going to do. And why are we doing this? Well, schools when we think about matching problem, with strict preferences and strict priorities, it has this set of stable matchings. It has a nice lattice structure. Among all those ones, we can pick one that actually is optimal for applicants or for students. Right? That's what we do. But in reality, the question is, why should we pick this assignment? Maybe we want to pick something that's going to produce a stable matching, that's going to produce a better outcome in terms of match quality. That's the question. But the question is a little bit more complicated than this, because in our problem, especially in the school choice application, schools categorize applicants into a very few priority groups, like based on neighborhood or sibling status. In Boston, for example, these are pretty much only two categories that define a student's priority. If you have a sibling attending a school and if you live within the neighborhood of that school, you usually used to get a very high priority in the past. Now things have changed a bit. If you only have a sibling, you would get the next highest priority. If you are living in the neighborhood, you would get the next highest priority, and all others would be ranked below below those students. Well, this actually creates a very large and complex set of stable assignments. And this gives us, this allows for scope to implement policies over the whole match. That's what we are after. We are going to look at the whole set of stable assignments, and we are going to try to pick one that actually optimizes other types of policies that actually maximize the total sum of match quality. And in practice, this has never been done before. Well, in practice, this has never been done systematically before. The usual procedure is the districts use a student proposing default acceptance algorithm with random tie breaking. My question here there is, why random tie breaking? If we have a match quality between student and his or her assigned school, why don't we use this information to get a better match? Why do we waste that information? That is really the question. Examples are, for example, minimizing the busing cost. That is a big question that used to be a big question in Boston from day one, we started working with Boston. That was one of the main questions. How can we assign kids closer to their home? Because busing kids is a big, major budget item. And that question has always been in their mind. And actually, lately they have even changed their admission system, probably because they wanted to reduce busing costs. Another alternative might be to maximize the total education production. If we know which schools work better for which type of students, why don't we use this information to maximize the total education production? Can I estimate this? To the extent that I can estimate match quality in terms of achievement or other educational outcomes between a student and a school, I should be able to do that as well. Now, a third one might be minimizing the average rank assigned school in student rankings. That is, try to assign kids as high as possible in their choice lists. When I told you, well, this is also something that we are gonna come back later in applications, and I'm gonna show you some numbers there. Now, while stability requires a pairwise comparison, match quality optimization considers the whole match. So it's a totally new question in this regard. What we are going to offer here is really a practical match quality optimal algorithm that's going to be polynomial in the number of students, but unfortunately exponential in the number of schools. How are we going to do that? We are going to do this by characterizing a subset of stable assignments through admissible schools, which I'm going to define next. Then once we define this, this is going to allow us to formulate the problem as a minimum cost flow formation. And this is a problem with the well-known solutions, and we are going to apply that. Unfortunately, we are not going to be able to solve for the global optimum in problems in which we have 30 or more schools, but I'm going to offer a local optimum, which is going to get very close to the global optimum, which we can show via simulations. So a quick overview of the results in applications. When I apply our match quality optimal algorithm, what do we get? On average, New York City kids can be assigned about a mile closer to their home. The middle school students, when we take into account match quality between a student and a school in terms of math achievement and reading scores, the students' math and reading scores can be increased by 3 to 5% of standard deviation on average. And if we try to optimize by trying to assign kids as high as possible in the choice list, we can actually assign about 10% more applicants to one of their top two preferences, the top two choices. Remember, these are all subject to the constraint that the matching has to be stable. Let me stop here and let me actually put an important remark. When we do this naturally and unfortunately, we are losing strategy proofness. We don't know of any mechanism that could actually improve over default acceptance with random type breaking in a meaningful way without giving away strategy proofness. So it is not surprising that we are not going to have the strategy proofness result here. But on the other hand, it's not also easy to imagine how a student would manipulate those mechanisms without knowing a lot of information either. So let me put the elephant out of the room first, and let me stop here and let me check if the question is clear before going ahead with the theory.
I have a question.
Yes, go ahead, please.
So I'm trying to understand how to frame the problem. So there is a sense in which things like distance or the scores might enter preferences directly. And that's why you like some school more than others. But you seem to think about those as potentially additional objective, where minimizing, for example, travel distance matters on top of how much that affects students' preferences directly. You think
That's a
about it
great
that
question.
way?
That's a great question. So there are two dimensions here. One, how do parents form their preferences? When they form their preferences, we know that they actually take into account the distance. They don't want to commute long distances. That's what we know. Given this, they actually form a preference list. In that preference list, they also rank schools in a preference order. If they are truthful, that already tells us what their first choice is, what their second choice is, what their third choice is. Now, given this, on top of that, the school district, a third agent here. The first family is the second schools in a two-side matching, and a third agent, the school district, might have a preference over the whole matching. What is this preference? Well, our first constraint is it's going to be stable with respect to student preferences and school priorities. Student preferences might be, and they are going to be impacted by distance, of course. But on top of this constraint, the school district also wants to pick a stable assignment that is going to optimize over their match quality, whatever it is. That's right. As our applications is going to show, leaving this decision to parental preferences and school priorities and stability is not enough, is not going to be enough to optimize on that direction. Actually, when we talk about distance, this is going to be even become more obvious. So we are not the first ones doing this. This has match quality based assignment has been applied in child adoption, immigrant placement. There's also a literature on network flows for assignment problems. Our work is more closely related to that. There's also a literature in computer science that tries to solve these problems using integer programming. Unlike these problems where you don't always get a solution, we are always going to get a solution, and our solution is going to be pretty fast, actually, much faster than your solutions. So here is the model. We are going to have a set of students S, a set of schools C. Each school is going to have a capacity. This is the number of seats. For this talk, we are going to assume that there's enough number of seats so that we can sit all the students. We are also going to assume that all of the schools are acceptable. That is why all of the schools are going to be filled up to the capacity. But these can be easily relaxed, not serious constraints at all. We are going to have a preference ranking of students. This is going to be a strict preference ranking. We are going to have priorities. That is the priority of student S at school C. We are going to number them from 1 to K. The smaller, the better. The smaller number means a higher priority. Let us keep this in mind because we are going to use those priorities to define admissions cutoffs. And those priorities are potentially weak. Well, if they are not weak, if we have strict priorities, the problem becomes so simple because with strict priorities, we know how to turn the set of stable assignments into a set of constraints in a linear programming. And then we can actually solve this problem easily. But with weak priorities, we are not going to be able to do that. And the problem is going to become much harder. In addition to this setup, we are also going to introduce a match quality. What's match quality? It is something specific to the school and the student together. When I am assigned school A, I might deliver a different quality than when Antonio is assigned school C. Now, what am I gonna do? Well, I'm gonna focus. These are the standard definitions. I'm gonna talk about an assignment. It's gonna be a mapping. It's going to assign each student to a school or leave him or her unassigned. Each school is gonna get a subset of students without exceeding its capacity. And a student is assigned a school if the student is in the assigned set of the school. These are the typical definitions. And the standard definition of stability. Well, first of all, it has to be individual rational. Then there should be no blocking pairs. A student and school pair is not going to block the matching in the following sense. The student prefers school C to her match, and she has lower priority than another student that is already assigned the school. We don't want such blocking. And what do we want to do? We would like to maximize match quality, sum of match quality among all stable matchings. We would like to pick a stable matching, mu star. That stable matching is going to maximize the sum of match quality over the set of all stable matchings. That is the problem. That's the problem that we are trying to solve. This is the addition, our addition to the otherwise standard two-sided matching problem with weak priorities. Unfortunately, this problem is not easy to solve. Finding a match quality optimal stable assignment is an NP-hard problem. This is where we start, and this is how we are going to proceed. We are going to just a second. We are going to characterize the stable assignment via admissions cutoffs. We are not the first one to do that. Once we characterize this via cutoffs for any cutoff vector, we are going to find an alternative set. First, we are going to look at the set of stable assignments which produce the same cutoff R. Then we are going to find a bigger set that's going to be easier to incorporate into our linear programming. Once we do that, we are going to formulate the problem as a minimum cost flow optimization problem. That's how we are going to proceed. What do I mean by all that? Let's see what I mean by that. First, let me talk about cutoffs. What's a cutoff? Well, here is a school with 5 seats. Here is our priorities. We have priorities from 1 to 5. Only 2 of the seats are filled up. The 3 seats remain unfilled. So we are going to set the cutoff, admissions cutoff at that school to the maximum priority 5 plus 1, which is 6. What does this mean? This means any student with a priority less than 6, if they want, they can get into that school. That's what it means. And actually, this means any student can get it because our maximum priority is 5. It's going to be less than 6. If the school is filled up, here's another school with 5 seats. There's 1 student with priority 1, 2 students with priority 3, and 4 students with priority 4. All seats are gone. And the cutoff here is going to be the cutoff, is the priority of the lowest priority among all the students who are assigned. In this case, it's going to be number 4. Any student who has priority 3 or less, if they want that school, they would get into that school right away. If any student who has priority 4 is not guaranteed to get into that school, that depends on how the ties are broken. And students with priority 5 cannot get into that school even if they want it as their first choice. So this is how I define the cutoffs. Once I define this cutoff, I'm going to define every stable assignment is going to produce a cutoff. And I'm going to consider the set of stable assignments that give exactly the same cutoff. That's what I'm going to do. And for this for this presentation, I'm going to assume that all schools are acceptable for all students. There are not enough seats for all students so that all schools are filled up. And then what am I going to do? I'm going to do the following. Here is the cutoff for school C. I'm going to fix a cutoff vector R. This is going to be one cutoff for each school in this set. And I'm going to define the set of admissible schools for student S given cutoff R. What is that? This is first, a school is going to be admissible if the student has priority that is less than or equal to the admissions cutoff. Which means if the student applies to school C, she has a chance to get in. Actually, if her priority is strictly less than the cutoff, she would get in for sure, right? But that is not enough. I need to make sure that she does not have a better school, a school that she prefers, and she has actually priority strictly less than that school's cutoff. Why? Because if she had such a school, she would get into C prime. For sure, she would never consider school C, which she ranks lower. And I define the admissible schools this way. This is really the set of schools that we need to consider. Given a vector R, let's suppose that we know that R generates a stable matching. Right? We need to only consider those alternative schools in this set of admissible schools for every student. But here is the catch. I'm going to define another set, potentially a bigger set, which I'm going to call it A bar. This is the set of assignments such that each student is assigned a school from their admissible schools. Well, do I know that this assignment is stable? Actually, I do. All the assignments in this set, extended set, are going to be stable. And this set is going to be a superset of stable assignments with a cutoff vector R. And now this set is going to be much easier to incorporate in my optimization problem. How am I going to do that? What's my optimization problem? Here's the optimization problem. I'm going to now put students and schools into vertices. On the left-hand side, I have students. On the right-hand side, I have schools. For each student now, given a cutoff R, for each student, I know their admissible schools. Student 1 has only one admissible school, B. I'm going to draw an arrow from 1 to B. Student 2 has two schools in his admissible set. I'm going to draw an arrow to each of those schools, A and C. Student 3 has only one, and student 4 has three admissible schools. These are the arrows. Now, I am trying to pick one arrow for each student on that graph. That's my optimization problem. But when I do that, I would like to maximize the sum of match qualities. What are those match qualities? This is what I am going to put on those arrows. If 1 is matched with B, she's going to gain 3. If 4 is matched with B, he's going to gain 2. These are the numbers. And I'm trying to pick arrows in a way that I'm going to maximize those numbers. But I cannot pick it in arbitrary ways, right? In this case, for example, I cannot pick the highest ones. 4 here, 3.5 here, 3 here, 5 here, 3.5 here, 2 here, 3 here. Because we also have to make sure that the capacities are respected. How am I going to do that? I'm going to put a capacity constraint on each vertex. Any supplier, in this case, students are going to supply 1 themselves. I'm going to put a capacity of 1, positive 1. Any receiver is going to have a negative capacity. For example, here, school A has a capacity of 2. I'm going to denote it as minus 2. School B has capacity 1. I'm going to denote it as minus 1. So this is my notation. I'm going to denote those as Q, or actually in my formulation, I'm going to denote them as L. And how do I formulate my problem? This is how I formulate my problem. L, E. E is the arrow between student S and school C. This edge is going to have a match quality, which I'm going to denote by L. I should have called this Q. And I'm going to pick a function Fe. This function is going to take values between 0 and 1. It can be fractional. If it is 1, it means I am picking this edge. If it is 0, it means I am not picking this edge. Now, here is the capacity constraint. For each vertex, if I am a student, this is from student to schools. This is the number of me that I am giving to schools. And this is schools to students. From schools to me, this is the number of schools that they are giving me. This eventually this how much resources I am going to end up with, that should not exceed my capacity. That's the capacity constraint. And this is our minimum cost flow formulation. Fortunately, this problem has a solution, polynomial time solution. These are there are many ready-to-use packages. We can use those. When we do that, what do we get? For each assignment in AR, for example, first let us justify our solution. There is a 0, 1 valued, integer valued f function satisfying the constraint. And each 0, 1 valued function satisfying the constraint corresponds to an assignment in our AR. So this actually gives us a valid formulation. And we also know that every assignment in AR is a stable assignment. And the minimum cost flow problem can be solved in polynomial time. And that's what we do. And this gives us an integer solution. For each cutoff, what are we going to do? We can solve the minimum cost flow problem easily. But searching through each cutoff is exponential and it's not computationally feasible. So to solve for the global optimum, we have to solve for each cutoff. We cannot do this. What we do is instead we are going to give you a local optimum. We are going to start with deferred acceptance with random tie breaking. This is going to generate a stable assignment. That's also going to generate a cutoff. Then we can start at that cutoff. Using this cutoff, we can go back to our linear programming problem, solve the optimal one, call it local optimum. This is what we are going to find. But later, if we want to search through all cutoffs, we don't have to do the search through all cutoffs. We are going to bound the cutoffs from above and below. Cutoffs that can give us a stable matching. And then we can actually do a brute force search, and we can do this with 30 or less number of schools. And this is actually what the most American school districts have. Let me stop here for a while, and let me see if you have any questions.
Atila, there are actually 2 questions in the chat. The first one is from Xuang Yang, who asks, what about no additive objectives? For example, I want each school to have a certain ratio of black to white students.
And certain ratio of black to white students. I'm not sure if we need. I think this is a different problem. This is also a problem that Aram and I have been working on a separate project. I think Aram presented it here as well, reserves and quotas. I don't see the objective function here. If the goal is to meet certain ratios, black-white ratios, it's not necessarily. But if you have an ideal point like in Ekenik and Yenmez, an ideal point of distribution across students, and if you are trying to get as close as to this that ideal position, This probably can be formulated as a linear programming too, but I have to think about that problem. What's the next question? And I'm noting this question. Thank you very much.
Vinay, you can ask a question if you want.
Olivier, you said two questions.
Yeah, but the person who has a question say what that he would like to ask him himself.
Okay. Then make sure check the chat.
Okay, otherwise it's just in the chat.
Okay.
Okay, I can read it. Can we have something which will also look at the quality of students that a school gets? Something like defining matching quality for match pairs from the perspective of both schools and students.
I'm not sure if I understand I'm not sure if I understand that question. Please feel free to jump in and try to clarify. This match quality, the way I form it, does not have to be like what the student gains. This can also be what the school feels. The school this might actually represent a cardinal valuation of the school for the students. If that's what you mean, we can handle that one. If
Yeah, so,
that's not what you mean,
yeah, sorry. Actually, in the graph that you showed, you have just, when students to schools, the graph that you have shown then of the match that the students, for example, has, yes, in this graph. So I was wondering if there is some, for example, students too have two possibilities of A and C, wherein the weights are 2 and 1.5. So is there a possibility, for example, that is this too also taking consideration of that A will get two students two, and then it will be kind of two for both the perspectives. So here we are only looking at the perspective from the students and then increasing this match quality. So if we also look from the perspective of the schools, like, and they also have some desirability as in the last questions as well. So are we going to handle that as well? So this.
I feel like you are proposing a much more sophisticated problem, a nested one maybe here.
Yes.
Yeah,
Yes.
no, we are not handling that one here.
Okay.
Can it be done the same way? Probably, but I don't think that would actually introduce further computational complexity.
Yes. Okay.
Yeah, but that's thank you. That's also another interesting question. So this problem can be solved in polynomial time, and for each cutoff vector we can solve this, but we cannot do the global search. Instead, we run a deferred acceptance with random tie breaking, and then we start there and we optimize on top of that. And what do we get? Let me show you what we get here. The first one is about distance minimization. Data comes from New York State. New York State is the biggest, largest school district in the US. There are about 1 million students every year that attend a public school in New York City. About each transition grade has about 70 to 100,000 kids going through the centralized admission systems. The transition grade is 6th grade in the middle school, 9th grade at the high school level. Here at high school level, for example, in 2011, the average distance between a student's home and the schools he or she ranks is about 4.5 miles, and the standard deviation is 3.3 miles. This is a huge standard deviation. It actually tells us that there's a big scope of minimizing distance here, and that's true throughout the years. And when we run 3 alternative mechanisms, that's what we obtain. We are first going to run deferred acceptance with random tie breaking. We are going to do this 100 times, and we are going to look at the distance of each student between their home and the assigned school. Then, starting with this, we are going to do our local optimization, match quality optimization. In our match quality optimization, the match quality is going to be the negative of the distance between a student's home and their school. And alternatively, we are also going to run a quite intuitive default acceptance algorithm where we are not going to use random tie breaking, but we are going to use distance as tiebreakers. So if Olivier and I tie at school A, if we have the same priorities, Olivier is going to be ranked higher if Olivier lives closer to the school than I do. That's what we are going to do. When we do that, the default acceptance with random tie breaking assigns kids on average to a school that is 3.8 miles away from their home. The intuitive one, the intuitive tie breaking with the distance, which we call match quality tie breaking. We use match quality to break ties. This reduces the distance from 3.8 to 3.1. But when we do match quality optimization, it further reduces to 2.75. So we get a reduction of more than a mile on average for each student. And this is pretty consistent over the years. Here's one potentially interesting, but probably much more complicated problem. We do this in a very naive way, right? These are driving distances. We think of students going to schools on their own here, and we are minimizing their travel distance. But in a city like Boston, it is actually the busing cost that they are trying to minimize. So the question is actually complicated and bigger than this one. They are going to look for stable matching that actually minimizes the busing cost. So we are going to have traveling salesman's problem subject to the stability constraint there. Can we solve this? Probably we can. It's definitely not in polynomial time, but maybe we can obtain similar polynomial time solvable, approximately optimal solutions. The second application is maximizing the education production function. What do I mean by that? I mean, some schools are actually better at training low achievers. Some schools are better at training Hispanic kids. Some schools are better at training some other types of kids. So one size does not fit all. If that's the case, if there is a match quality in terms of training and achievement, how can I utilize that? Well, the first step should be we need to have a match quality in terms of educational achievement. There are many models, value-added models, that try to estimate this. The purpose of this paper is not to dive into this big value-added models literature. Instead, we use a very simple model here that's very common in the literature. This is the educational outcome we are interested in. This is, for example, the math score of student S if she attends school, she's enrolled in school C. This is the impact of attending school C. And this is the match, kind of match specific effect here. The impact of student specific effect of attending school C. And this is the error term. We estimate this, and our estimated match quality is given by this predicted value. What do we use here as XS? These are the student covariates. This is whether a student is the student's gender, the student's racial and ethnic background, income indicator, And this is incredibly important. Baseline test scores. Baseline test scores make those models pretty robust in the WAM literature. When we do that, we get a predicted value for the match quality. And when we do this, here's what we get. In terms of math, when I break the ties by using match quality, this is the intuitive one. By the way, the deferred acceptance with random type breaking is normalized to 0 in this exercise. So these are the gains on top of deferred acceptance with random tie breaking. If I break the ties by using match quality, that actually improves students' achievements up to about like in 2017 to 18, like 1% standard deviation. But if I do, excuse me, match quality optimization on top of deferred acceptance with random tie breaking, that actually increases math achievement by 5% standard deviation. And that's a huge increase. What does this mean? This means the achievement gap in the white and black achievement gap in the US is huge, and it's about 7% standard deviation. Look, our gain from match quality optimization is actually 5%. This is a pretty significant gain. Finally, there are many stable assignments, but we may want to pick one that actually assigns kids higher in their choice list. When we do that, or when we do the other ones, we know we are going to lose strategy proofness, right? But that is a real problem for applications. There are districts who actually aim to increase the rank of assignments in their admission systems. When we use the ranking of student of a school as the match quality, this is what we get. The random DA with random type breaking in New York City, on average, assigns kids to their about third choice. When I break the ties by using this student ranking, that actually assigns students slightly better. It decreases the average rank from 2.9 to 2.8. But this still requires some randomness, right? Because Sander and I might be ranking the same school as our second choice, and we might both have the same priority. What does this mean? Then we are both going to have the same match quality, so we might need some randomization here. This includes some randomization. When we, this one slightly improves the average rank. When we do match quality optimization on top of deferred acceptance with random type breaking, we actually get a pretty good improvement. It's about like 0.7, close to about 1 higher choice. This is among all students when we assume that all unassigned students are assigned to their last choice plus 1. When we do the same exercise among all assigned students only, get rid of the unassigned and look at the assigned, the results are pretty similar and actually much more impressive. So this is what we obtain when we apply our methods. That's actually, I'm running out of time. Let me briefly talk about global optimization. It's NP hard. For 30 schools or less, we can actually find the global optimum. How do we do that? We actually bound the cutoffs of stable assignments. We offer new algorithms, deferred rejection and deferred proposal. For example, deferred rejection does the following. Like in the applicant proposing the deferred acceptance, every student applies to their first choice. Usually, the schools actually admit up to their capacity, but this time, schools look for the students up to their capacity. If that student has priority 3, the school rejects priority 4 and higher students, but keeps all students with priority 3 and less. This may actually exceed their capacity. That's how we do it. And this is the relaxation there. We also have a deferred proposal algorithm. This actually bound this set of cutoffs that can produce a stable matching, and then we can search within this cutoff that can work for 30 or less schools. And simulations with 30 schools show that the local maximum, the way we do it in our real data applications, actually gets very close to the global maximum. So let me stop here for questions before running out of my time.
I have a question.
Yes.
So the kind of the simple way to incorporate match quality where you use it as a tiebreaker gives you some improvement, but not a kind of maybe sometimes it goes halfway through the whole thing. I guess there is a problem with the unit of measure, but one way to think about the problem would be imagine that you tell the school you have to pay for commute. So then effectively you incorporate the match quality, imagine that's distance into their preferences. And I wonder how far that would go in terms of addressing the issue of. So I guess the way you want to think about your problem is that the schools are internalizing some impact of their choices. For example, they don't pay directly for busing. Then the typical way I would imagine to address it is, okay, let's make the school pay for buses. So then their budget goes down if they admit students that are very far away. And so then would be a way to introduce the caring about match quality, if that's distance, directly into the priority of the school.
Yeah, that's a good point. Actually, a better application in our case would be the Boston data. In Boston, actually, the school district pays for busing. In New York City, too, New York City actually gives Metro cards to students, and students can use those Metro cards, reduced price Metro cards. When you introduce, let's not forget, this is market design exercise without monetary transfers. We don't have any money here. When we introduce money, when we say they have to pay for the distance, why is this different than not providing busing at all? I think that the question boils down to the following. If we do not provide busing, how would parental preferences change versus if we provide busing? I don't have an answer for this question, but to your question, I really don't know why this question would be different than a problem in which the city or the school district does not pay for busing and families take care of it themselves.
No, I think I guess then maybe the first question would be, how do you think about this match quality? That who is minimizing the commuting distance? What does it stand for? One way to think about it, the parents still don't like their kids to go far from home, but they don't pay monetary the cost of buses. So then, and schools don't either because it's the school district. So then nobody does that. And so you need some extra layer of a third agent, which is the school district, who tries to respect stability, but they care about how much money they're spending on buses. If I think about that is an interpretation for why we need the extra layer, for example. In that world, then making the schools pay directly would add an extra way in which distance matters above and beyond the disutility the parents suffer. Similarly, it could be some other interpretation for the match quality. And in a sense, I would like to think about how much we can bring this extra layer into the rank ordering of agents in the market. And how much instead this global problem on the outside instead essential because the agents will not be able to internalize the cost of their choices.
I see. So, Paula, actually, our motivation is exactly what you said. There is a third agency here that actually cares about the distance and that tries to minimize that cost. That's our motivation, really. Your question is how much of this can we internalize? Actually, we can internalize it fully. There are ways of, I don't know if that's the answer you are looking for, but the optimal solution can be implemented as a deferred acceptance with optimal tie breaking, if that's what you're asking for. But that's, in my opinion, kind of a very indirect way of addressing the question. We can do it this by optimally breaking the ties, then apply deferred acceptance. That for me is the answer to your question. We can actually embed those preferences into tie breaking.
I see.
So if I may, hi Atila. Hi
Hi.
everyone. First a clarifying question. So you can do an allocation with a random tie breaking and then improving on the distance by solving in different cycles. That will be what you are doing. That and the solution for that process will be the optimal tie breaking, or will be a different procedure.
Antonio, could you repeat your question? I would like to answer the right question, not the wrong one.
I was wondering whether if you start for a random tie breaking and an allocation that is stable under this random tie breaking, but you take into account the indifferent class because you are using an arbitrary tie breaking, and then start doing improvements like erging cycles by reducing the distance, will you end up in an allocation that will be the same and if you use the optimal tie breaking for the beginning, or it will be different?
That's interesting. We haven't thought about that. I'm not
You
sure,
have
but
a big
we
indifferent class,
might actually arrive starting from the outcome of the deferred acceptance with random tie breaking. We might actually look for swaps among students, stable swaps.
That's right.
That actually minimize the distance, and then that can also improve their matching. Can we arrive to the locally optimal one?
Right.
I don't think so. But we are working on a separate exercise right now. The solution of that, I think, can be obtained via yours. But let me first tell you why I don't think so. Because our solution does not guarantee that every student is going to get a better school when we optimize on top of deferred acceptance with random tie breaking. And Ergin and Erdil, actually, nobody gets worse off. They all improve. Right? So I don't think that's what's going to happen. But here's what we are working on right now. It is easy to incorporate that feature into our optimal linear programming. Can we look for Pareto improving solutions that are match quality optimal? That only requires one small change. You remember when I defined the admissible set of schools. In that admissible set of schools determines which schools from which student to which schools can I draw an arrow. In that set, the only constraint is going to be those schools have to be either the student's assigned school or a better school. This is an exercise that we are working on right now. And in that case, maybe your conjecture is true. Maybe the Pareto improving match quality optimal solutions can be found via something like Ergin and Erdel cycles.
Okay, thank you.